So now we've introduced the idea of thin film interference to an example problem. So let's suppose that you are using a laser, and the laser has a wavelength of 650 nanometers, and you want to focus the laser using a lens. Now, the problem is that if it's a high-powered laser, when the laser hits the lens, some of the light's going to be focused, but some of it's going to be reflected, and you don't want it to reflect. So you don't want to lose any energy. You want all of the laser light to be utilized. You want all of it, so you want to minimize reflection. So what you do is you can put a thin film on your lens. So on your lens, you put a thin film of thickness L. Now, if the thin film has an index refraction so the index refraction of the film, let's say, is greater than the index refraction of air, but less than the index refraction of glass. Okay, index refraction of glass depends on the kind of glass. Let's just say about 1.5. Index refraction of air is approximately 1. And so it just has to be in that range somewhere. If that's the case, then you get a phase shift on both the inner and the upper and the lower surface of the thin film. So if you want to maximize transmission, that means you want to have the most light going through the lens. That means you want to have minimum reflection. So you don't want any of the light to be wasted in reflecting. So these two statements really mean the same thing. Minimum reflection means maximum transmission. If we have maximum reflection, that means the least amount of light is going to go through. And so we want to minimize reflection. Now, since we've said that the index refraction is between that of air and the material, that means we get a phase shift on both sides. So minimum reflection, that would mean destructive interference. Okay, that would mean that we would say that 2L equals m plus 1/2 lambda over n. Okay, so we need to know what the n is because it makes a difference. Okay, so let's assume n equals 1.4. I'm just pulling that number out of the air. It depends on what material you use. So we're just going to assume here n equals 1.4 because I'd have to give you that. So that's not just something you would know or you'd look it up. You look it up in a table somewhere or I'd give it to you. So m equals 1.4. So that means we can plug that in up here. Okay. So I want to know the thinnest that this film can be. You know, the thicker the film, the more uneven it's likely to be, the more problems you have. So normally you want to put the film on there that's the thinnest possible, the fewest a little layer that's the fewest number of atoms, fewest amount of material. So we just do a little algebra here. Okay. So L equals m plus 1/2 lambda naught over 2n. Now, the thinnest it's going to be would be if m is 0. So L equals lambda naught over 4n. So that'd be 650 nanometers divided by 4 times 1.4. Okay. And so that would give you 116 nanometers. So that's the thickness of your film. Now, is that the only possible thickness that would work? Well, no, that's not the only possible thickness to work. There are other possible thicknesses. This is the thinnest that it could be. What else could it be? Well, that would be if m equals 1. So if m equals 1, So L equals m plus 1/2 lambda naught over 2n. So if m equals 1, okay, then 1 plus 1/2 is 3/2. So that would be 3 lambda naught over 4n. So in that case, the thickness would come out to be 348 nanometers. Okay. Likewise, m could be equals to 2. Any of those would work. In depositing a thin film, though, it's often a bigger technological and engineering problem to lay a thick film than it is a thin film. So the thinner the film, typically the better it is. Now, this is actually an application not just lasers, because with camera lenses, you don't want light reflecting off the camera lens. So what you would do is you could put thin films on here. One film, they could be different indices of refraction. So one film actually minimizes reflection for one color. Another film minimizes reflection for another color. You could have multi-coatings on here. In fact, if you buy binoculars or camera lenses, it would say coated lenses, coated optics, meaning that they've got a coating on there, and that does improve transmission. Okay, typically if you have multiple coatings on there, that improves transmission over a wider range of colors. Now, often they make a decision that certain colors are more important to transmit than other colors because your eyes or optical instruments are more sensitive to one wavelength than the other, so you care less about getting that wavelength through, but other wavelengths are less sensitive, and so you want to have as much of it go through as possible. And so you'd have multi-coated optics. And so there's little tricks to how they label this, because sometimes they only put the optics on some of the surfaces. In some cases, all surfaces have optics, have optical coatings, and so forth. But because the coatings are very, very thin, if you get dust or something on the lens, you cannot just take a wipe and wipe it, because that would scratch the coating. And then, of course, if you scratch the coating, it's no longer the right thickness. And so you have to be very careful when you clean coated optics that you don't scratch the coating, because the coating is actually there to minimize reflection and maximize transmission.